You learned solubility rules when you were doing precipitation reactions. Precipitation reactions. So we applied these solubility rules, which we're going to call guidelines now, to the ions in solution to determine if you have an insoluble product. So in a precipitation reaction, that's what we did. And I would look at all of these ions. I have lead ions here, I have nitrate ions here, I have sodium ions, I have chlorine ions, and then I'm just going to look at my pairings. Is any of these going to form an insoluble product? So this would form sodium nitrate, which is soluble, but my other product would be lead 2 chloride, and I know from my solubility rules that that's going to be my insoluble product there. And so my precipitation reaction, I would say, yes, this is a precipitation reaction that has occurred because I formed an insoluble product, and I would apply those solubility guidelines to that. So we're going to build on that here in this chapter, and we're going to call this selective precipitation. So it's this idea, this concept of just looking at what ions do you have in solution, and are you going to be able to form an insoluble product? I'm going to apply that here. If I want to precipitate an ion, maybe I'll add something to that that I know will react with that to precipitate it out. And this is often helpful in a laboratory standpoint if I want to remove lead ions from my solution, for instance. I'm going to add enough chlorine ions so that I form an insoluble product, and I'm essentially removing all of these lead ions here. If I want to force it so that it all comes out of solution, then I'm going to add I'm going to add chlorine ions in excess so that I'm sure that I'm precipitating all of my lead ions here. So that's selective precipitation. It would be a strategy that you use in the lab to get rid of an ion that's in solution that you want to be able to remove. Because once I precipitate this into a solid, I can spin that test tube down, I can pull my supernatant, and my liquid is no longer going to contain any of those lead ions because they will have all precipitated out. The trick is that I have to add an ion in that's going to precipitate the ion I want to remove, and I have to add this in sufficient amount of quantities to remove all of that lead ion. This, if I form this, can become an equilibrium scenario. So I want to have a lot of chlorine ions, so I'm shifting that reaction back to my undissociated reactant here. So I have a couple of things. I want to add an ion in that's going to react with an ion of interest and precipitate it, and then I want to have enough of this there so that it pushes this effectively to the right completely. So how do I know how much I need? I'm going to go back, and before we start this, I'm going to talk about Q and K again. So remember, Q is our reaction quotient, and I told you that it's going to come into play kind of throughout all these equilibrium scenarios because Q allows you to take values for species, whatever substance you have in your equilibrium process or your equilibrium reaction, and determine if it's at equilibrium, or if not, which direction the reaction is going, right? Is it going forward or is it going in reverse? I'm going to apply this to KSP. So if Q equals KSP, then I'm at equilibrium and I have a saturated solution of my ionic compound. What that means is that no more of that substance is going to dissolve because it's saturated. So if I can determine Q and I know my KSP because I can look those up in a table, then I know if I'm at the saturation point. If Q is less than KSP, then I'm unsaturated. I'm not at equilibrium. And my product, I'm going to favor the forward direction and product, which means that more of that substance will dissolve. If I take something and I add it in and I have a Q that's going to be less than KSP, then whatever I'm adding in, that's going to be able to dissolve into water. If my Q is greater than my KSP, now I'm supersaturated. I'm not at equilibrium, and I'm going to favor the reverse direction and my reactant, which in this case is my solid. And so I'm actually going to see solid precipitate out. So I'm going to see a solid precipitate out because I'm over that saturation point. So where this is going to come in handy is in the selective precipitation. All right, so let's go back to our look at this precipitation reaction. Actually change this to bromine. If I add these together and I have sufficient quantities of both of them, like I said, I'm going to see a precipitate. And then I'm going to see NaNO3 stay in solution. So this would be my insoluble product here. But it's only going to be insoluble. It's going to depend where I am here. If Q equals KSP, I'm going to be at equilibrium. If Q is less than KSP, then I'm unsaturated. I'm not going to see any solid. If it's greater than, then I'm supersaturated. That's where I'm going to see that precipitate form. So just because I have a solution of lead nitrate and I mix that with sodium bromide doesn't necessarily mean that I'm going to see a solid form here, because it's going to depend on how much of these I have present and the solubility product constant of KSP. For my insoluble product, which in this case is PbBr2, how much of lead ions and bromine ions are in that solution. And that's where I'm going to find Q, and that's going to tell me. I'm going to compare Q to KSP, and that's going to tell me if this is going to precipitate or not. So let's say here this solution is 0.0150 molar solution, and this solution here is 0.00350 molar. So I have these two solutions, and I'm going to mix them together. In sort of normal Gen Chem 1, you would have said, okay, mix them together. You probably would have ignored these values completely, applied your solubility rules, gotten here and said you'll form an insoluble product. But now, since we're in Gen Chem 2, we know that there is a KSP for potassium bromide, and so a small amount of these ions are going to remain in solution. They're not going to form an insoluble product. So I have to determine, are these sufficiently concentrated enough in both of the ions that it's going to push me into that supersaturated where Q is greater than K, and then I'll see an insoluble product. Only if Q is greater than KSP am I going to see that. So I'm going to set up Q first. So Q, remember, looks an awful lot like K for my solution, my insoluble product, and I'm going to plug these values in. So for every one of these that disassociates, I'm going to have one lead. So if this is my molarity of lead nitrate when this disassociates, this is also going to be my molarity of lead ions. This is my molarity of sodium bromide. When this disassociates, I'm going to form one bromine and one sodium. So this is also going to be the concentration of my bromine ion in solution. I'm going to ignore my stoichiometry here. My stoichiometry here is coming from my product. So I'm going to ignore this stoichiometry. I'm going to find this stoichiometry. That's my 2 here. That's going to give me a value 10 to the minus 7. I'm going to compare this to the KSP. So KSP for PbBr2, and this is going to be from the table, is this. So how does Q compare to KSP? Well, they're not equal. So it's not at equilibrium, but Q is less than KSP. If Q is less than KSP, then what I'm going to see is it's unsaturated, it's not at equilibrium, it's going to favor the forward direction, and the product, which is the free ions in solution, so I'm not going to see a precipitate. No precipitate will form. If I want to form a precipitate, I'm going to need to add each or one of the ions. So if I add more of this, that's going to make my Q higher. If I add more of this, that's going to make my Q higher. So as my Q gets closer to KSP and surpasses KSP, now that's going to shift the direction of that reaction. So I could add in more of both, or I could just add in more of one of the other ones to form my precipitate. So for these selective precipitation reactions, first off, figure out what is your solid, what's going to be if I take these two solutions and I mix them together, what is my potential solid that's going to be formed. Look up the KSP for that, then find your Q based on your initial concentrations of those solutions, then compare your Q and your KSP, and that's going to tell you if a precipitate is going to form or not. Oftentimes I want to separate ions from each other, so I'm actually going to do another calculation with you. Let's say I have a solution, 0.059 molar magnesium ions, so those are in solution, and a solution that has 0.011 molar calcium ions. By definition, giving these molarity implies that these are in solution, and I want to separate these ions, and I'm going to using potassium hydroxide. Because what do I know about potassium hydroxide is that that's going to be soluble for when I drop this into the solution, it's going to separate into potassium ions and hydroxide ions. Now if I have a solution that has magnesium ions and calcium ions, I have the potential to form magnesium hydroxide and calcium hydroxide, and those are going to be insoluble products. My product would be magnesium hydroxide, and here would be calcium hydroxide, and my KSPs, the first thing that's going to precipitate out is going to be my magnesium. So this has a smaller KSP, so it's going to precipitate first. If I continue to add KOH, I'm eventually going to start precipitating my calcium, but only after I've precipitated all of the magnesium. So this is another way to selectively precipitate an ion. Here I have two cations. I'm going to try to figure out how much hydroxide can I add in here to only precipitate magnesium before I start to precipitate calcium. And it's going to depend on these KSP values. So my question that I want to ask is, what concentration of KOH is needed to precipitate only magnesium hydroxide? So I don't want to add too much in, because what I'm going to see is this is going to precipitate out until I've used up all of my magnesiums, then this is going to precipitate out. And so my precipitate is going to be a mixture of magnesium hydroxide and calcium hydroxide, and I haven't selectively precipitated anything. I've just kind of dumped a whole bunch of hydroxide in there, and now I have a lot of precipitate. I want to have some finesse with this so that I add in only enough that I precipitate out the magnesium and I leave the calcium in solution. All right, so the first step for this I've already done is I'm going to find my KSPs here and determine which one is going to precipitate out first. So that was my first step. My second step is I'm going to use Q in a calculation, and what I'm going to do is I'm going to set Q equal to KSP in this, and then I'm going to solve for hydroxide ion concentration. I have magnesium concentration from up here. I'm going to use a calculation involving Q. I'm going to set Q equal to KSP. I'm going to solve for hydroxide ion concentration using my magnesium. That's going to tell me the concentration of hydroxide that I need to add to precipitate this. So I'm going to have to add in potassium hydroxide at a concentration of this to selectively precipitate my magnesium. I can take this one step further. So at what concentration? I know from here that at a KOH concentration equal to 1.869 to precipitate magnesium hydroxide. And let's say I want to know what concentration of KOH to precipitate my other ion. I'm going to do the same thing, only I'm going to use the KSP for calcium hydroxide, not magnesium hydroxide. So I'm going to do the same set of conditions. And my initial concentration of calcium was 0.011 molar. So I'm going to use those values. So I'm going to have to, at this concentration, I'm going to selectively precipitate out magnesium, but then I'm going to have to add in potassium hydroxide concentration at this to start precipitating out my calcium. How much magnesium ion is left in solution when calcium ion starts to precipitate? Right, because remember we have an equilibrium scenario happening with everything. So I have magnesium hydroxide solid that I'm forming by adding in potassium hydroxide, but I'm always going to have a little bit of equilibrium here. So when I get to the point where I'm adding in enough of this to start precipitating calcium hydroxide, is there going to be any magnesium left? I can calculate that by plugging in this concentration up here for my hydroxide and solving for magnesium. So I'm going to take my KSP, I'm going to use my new concentration for hydroxide, and I'm going to solve for magnesium ion concentration. So those are my steps. I'm going to take the KSP from magnesium hydroxide. I'm going to use my concentration up here that I found that is going to start to selectively precipitate out my calcium, and I'm going to solve for magnesium ion. That's going to tell me how much magnesium is left when calcium starts to precipitate, because calcium is not going to start to precipitate until the hydroxide ion gets to be this concentration here. So really small amount of magnesium is going to be left when calcium starts to precipitate. All right, we're going to switch gears now, and we're going to talk about metal transition metal ions and what's happening in a transition metal ion complex. We call this complex ion equilibria. It's something that you see, a phenomenon you see with transition metals, because they tend to be really good Lewis acids. And I'm not going to get into why that is, because like I said, we're going to cover that closer to the end of the semester, kind of at the end of the semester, why a transition metal is a good Lewis acid. But remember, our Lewis acid is an atom that is able to accept an electron pair. And because transition metal ions have lost electrons, they have empty d orbitals that can accommodate an electron pair from a Lewis base. And so anything that has a free electron pair on it has the ability to act like a Lewis base. Water can do that. Things that have ammonia in them, because nitrogen has a lone electron pair on it, those are all going to be things that can act like a Lewis base and complex with these ions. And together, a transition metal complexed with a Lewis base is going to be this complex ion equilibrium. But the tricky thing is that they don't usually just bind one, they'll bind many of them. And so here in this example, here I see silver ion, my transition metal, and I have to have lost electrons, so these are always going to be ions, transition metal ions, positively charged, complexing with water. So if I just have free silver ion in solution, it's really not free silver ion in solution. It's bound a couple of waters in this ion equilibrium complex where water is donating an electron pair to silver, and they're kind of hanging out together, and they form this complex ion. These are highly favorable. So from an equilibrium standpoint, everything that we've looked at thus far has been favoring the reactant side. So ionic equilibrium, only a little bit of dissociation. Acid-base chemistry, only a little bit of dissociation. This is the complete opposite. So when I form these transition metal ion complexes, they're highly favorable. So they have really large K values. Here is the table of these, and you see here 10 to the 21, 10 to the 33, right? Cobalt complexed with ammonia here, 10 to the 9, 10 to the 29, chromium ion with hydroxide. And so these have really high values. These are going to call KFs because F stands for formation. And we're going to apply it specifically to these metal ion Lewis base complexes. And you see here, there are many different types of Lewis bases. I have cyanide because there's a free electron pair on that nitrogen as well as the carbon. Ammonia is a great Lewis base because it's small and it has that lone electron pair on nitrogen. This is the oxalate ion. Even your ions like fluorine, iodine, chlorine, those can all form complex ions with metals. So you see here bromine, hydroxide we've already talked about, water can, this is the thiocyanate polyatomic ion. So these all are really high. You don't see any waters listed in here because what usually happens is water is kind of a weak Lewis base, and if I have anything other than water present, it's usually going to kick water out and form the complex ion with the metal over water. So if we just take silver again, if I just have silver ion in solution, and maybe it's from silver nitrate or whatever, and I have it in water, that aqueous denotes that it's in water, it's going to have this equilibrium that looks like this, where it's going to hang out with two waters. Water is neutral, so the charge is going to come over with it. It's still going to be charged, but it's going to be complexed with that water. So in solution, I think I have free silver ion, but I really don't. I have silver complex with water. My Kf for this, if I were going to write my law of mass action, it would look like this. And water is a pure liquid, so it falls out of the solution, silver ion here. That would be my Kf for silver complex with two waters. What happens if I add ammonia? So let's say I have a solution of silver, a aqueous solution of silver ion, which is really this guy here. It's really this guy because I'm favoring this, and I add ammonia to that. Now I'm going to form a transition metal complex with ammonia. It's going to kick the water out because this is a better Lewis base, and it's going to form AgNH3 2+. So now it's going to kick out those two waters, and it's going to form a transition metal complex with ammonia. My Kf for this is going to look like AgNH3 2. And don't worry about how you know if it's 2 or 4 or 6 unless you go back and look at your table that has your Kf values on it, and that might give you a clue. So if I go back to my table and I try to find ammonium complex with, or a silver complex with ammonia here, I'm going to find it here, and I see my Kf for this is 1.7 times 10 to the 7. And I only see 2 ammonias here. So I know it's not going to bind 4 or 6, and it's only going to bind 2. But if I have something like cobalt, then I'm going to bind 6. And so I'm going to look at this table to help me determine how many of these Lewis bases are actually pulled into that complex. So I'm going to look and see if I have a Kf value for copper with ammonia. I do. Oh, it has 4, so that's going to be my complex that's going to be formed. So the larger the Kf value, the more favorable that formation of that complex is. So if I had, instead of ammonia, or let's say in addition, let's say I also added in cyanide ion, then I would form, this is negatively charged. I'm going to have 2 of them. So that's going to balance out this positive charge. So now this ion becomes negative. I look up my Kf value. That's going to give me a Kf of 1.0 times 10 to the 21. So what that tells me is if I have silver ion in solution, if I haven't added anything, I just have silver ion in water, this is going to be the complex that's formed. If I add ammonia to that, now I'm going to kick out that water and I'm going to form this complex here. If I take this and I add in cyanide, this Kf value is so much higher than this that this is going to form silver cyanide ion over the ammonia and kick ammonia out. And so as you increase your Kf values, that's going to favor your Lewis base. Because you're favoring the product, this also changes your ice tables. Okay, so I have these 2 solutions here. I'm going to mix them together, and I want to know at equilibrium what concentration of free nickel ions remains. So not complexed. So I have nickel ion, I have chlorine ion, and I have ammonia. I don't think the chlorine is going to do anything, but I'm going to look up and see if I can find a Kf value for nickel ammonia. And I'm going to find my Kf for nickel and NH3. And that's going to tell me what that complex is going to look like. So actually, when I look on my table, I have a Kf for nickel complex with 6 ammonia groups. And my Kf for that is 2.0 times 10 to the 8th. So that's my Kf value. I'm going to write an ice table because I want to know how much of this is free at the end. So I know what my initial starting concentrations are. I'm going to find my, I can't just take 0.0117 because I have, once I add this into a solution and I add another 175 milliliters of liquid in there, I've changed the concentration of these ions because it's no longer in 125 milliliters, it's in 300 milliliters. So I'm going to first find my new concentrations here. So that's my new concentration of nickel starting out. And I'm going to do the same thing with ammonia. 0.146 molar. My change here is my ice table is going to be different because my Kf is so high, I'm going to assume that my equilibrium is going to favor this side. So all of this, my assumption here is that all of this is going to react. So I'm going to lose all of this. I'm going to come back and find if there's anything left because I asked you to find what concentration of nickel remains at equilibrium, but then I just told you I'm reacting it all. I'm going to come back, so I'm not going to put that as 0, I'm going to put that as X. This is going to be 6 times my concentration of my least amount here. So there's much less nickel than there is ammonia, so this is going to limit the reaction. So my change here is going to be 6 times this amount, and then my increase over here is that amount. So this is going to limit my change here. This becomes 0.117 molar, and this just is. So I don't give this a 0. So this is not 0. Even though if I did this math here, I would get to 0. Because this is going to represent a small amount that hasn't associated in a complex. So it's not going to go to 100% completion because I have this guy here, even though I have a significant amount of ammonia here. I'm going to have a really small fraction that's going to be X that doesn't go into solution. So this is my leftover nickel ion after I've added NH3 to my solution. So a really small amount here. So we're going to do, actually in our Zoom meeting, we're actually going to do another type of problem where we're looking at these transition metal ion complexes where we have a common ion effect. And if I'm able to increase the solubility of an ionic compound by adding in one of these Lewis bases. And so we'll do that problem not in our pre-recorded lecture, but we'll do that problem in our Zoom meeting. This ends this chapter, and I will see you guys when we're doing problems.